All right, today we are tackling one of the biggest, boldest ideas for cleaning up global shipping, putting nuclear reactors inside giant cargo ships. Yeah, I know, it sounds like something straight out of science fiction, right? But it just might be the powerful, zero-emission solution the industry is desperately searching for. So let's get into it and see what it would actually take to make this a reality. So here's the deal. Right now, the entire maritime world is in a flat-out race against the clock. You've got massive financial penalties coming down the pike, stricter international rules, and it's all pushing for one single thing: get carbon emissions down to zero. For an industry that literally moves 90% of everything we buy using fossil fuels, well, that is a huge, huge challenge. And that leads us right to the big question. If you want to get to true zero emissions, you need an energy source that's incredibly powerful and doesn't spit out greenhouse gases while it's running. And wouldn't you know it, that's put nuclear power, an idea that was tried out and then shelved decades ago, right back in the spotlight. So first up, let's talk about why this idea is so attractive in the first place. What is the actual promise of having a nuclear-powered fleet sailing the oceans? Okay, check this out, because this is where it gets really interesting. First, you get zero emissions out on the open water. That's the main prize, right? But look at the other benefits. You get energy costs that are stable and predictable for years, completely unlike the crazy roller coaster of the oil market. And get this, ships wouldn't need to stop for fuel all the time. We're talking maybe once every 20 or 30 years. That would completely rewrite the book on how global shipping routes are planned. Now, I know what you're thinking. Hang on, haven't we tried this before? And you're absolutely right. But the technology being talked about today is a whole different ballgame compared to the reactors on old ships like the NS Savannah. Those were complex, super expensive, and needed massive, highly skilled crews to run them. These new concepts, things like Generation 4 reactors, are designed with passive safety systems. That means they can shut themselves down safely with no human help at all. They're being built for much smaller crews and, hopefully, much lower costs. And this, right here, is the real heart of the matter. The engineering? We're getting there. You can actually see a path to building these ships. The truly gigantic hurdle, the thing that will make or break this entire idea, is creating a global system to manage them safely and consistently. It's all about the rulebook. To build that system, we're going to need a global rulebook, a predictable, universally accepted set of standards that covers everything from how these ships are built to how they're taken apart at the end of their life. And here's the thing. Right now, that rulebook is basically a blank page. So what do we even mean by a regulatory framework? Well, think of it as the entire legal and technical architecture for these ships. It means that a ship built in Korea, fueled up in the Netherlands, and sailing to Brazil is operating under the exact same safety and security standards everywhere it goes. Without that, you just get a messy patchwork of different rules, and global trade can't work like that. So who's going to write this rulebook? It's got to be a team effort. You need the IMO, that's the organization that governs all international shipping, to lead the charge. But they can't do it alone. They'll need the deep technical expertise of the IAEA, which is basically the world's nuclear watchdog. And just as important, you need the classification societies. These are the independent groups that certify ships as safe, and they have to work together to create one standard approach, not a dozen different ones. And you've got to realize this framework has to cover the entire life of the nuclear fuel. I mean, everything. From the moment it's produced, to when it's installed in a reactor at a special port, to how it's swapped out years later, and finally what on earth we do with the spent fuel. Every single one of these steps needs crystal clear rules before even one ship can get a license. And let's be perfectly clear about this. Solving the what do we do with the waste problem is an absolute deal breaker. If there isn't a credible, safe, long-term plan for spent fuel, this technology will never, ever get the public trust or the regulatory approval it needs to even get off the ground. Okay, so beyond the rulebook, there's another absolutely critical concern: making these floating power plants practically indestructible. We are literally talking about building a fortress at sea. First off, you have the physical strength. These ships operate in some of the most brutal environments on the planet, so the reactor and all its containment systems have to be engineered to survive the absolute worst-case scenario you can imagine, like a direct hit from another massive ship or running aground at full speed. Next, you've got to think about the human threats. These vessels have to be secured against any kind of external attack. I mean, in a world with modern piracy and maritime crime, a ship carrying nuclear material is a target like no other. And the threat isn't just from the outside either. The security protocols have to be tough enough to prevent internal sabotage, making sure no one on the inside can compromise that reactor's safety. This is exactly why just being physically tough isn't enough. These ships also have to be digital fortresses. We're talking about constant 24/7 remote monitoring from a control center on shore, redundant communication systems that can't be jammed, and most importantly, ironclad cybersecurity to protect them from being hacked. This is just as much a digital challenge as it is a physical one. All right, so with all these massive regulatory and security challenges, what's the actual path forward? How do we get this from a cool idea to a commercial reality? Well, a huge part of the answer comes down to one word: standardization. Instead of designing a unique, custom reactor for every single type of ship, the industry needs to take a modular approach. Think of it like building with high-tech Legos. Standardized reactor modules that can be mass-produced in a factory, installed more easily, and approved by regulators way faster because they've already seen and certified the design. That is the key to bringing the cost down. And here it is. This is the magic number that researchers are pointing to. If the cost of building a reactor can get below $8,000 per kilowatt, nuclear power could actually become cheaper than other fuels, even if the rest of the industry doesn't completely decarbonize. This number makes the whole economic challenge feel real and achievable. But, and this is a big but, as this quote makes really clear, that upfront construction cost is only one piece of the puzzle. The entire life cycle cost, from the fuel to the maintenance to the waste disposal, all of it has to be factored in for the business case to actually work. It's not just about building the ship, it's about running it safely and economically for its entire life. So when you boil it all down, it comes to this: the technology alone is not going to get us there. Making nuclear shipping a reality is going to require a level of collaboration we've never seen before between shipping companies, tech developers, global regulators, and frankly, all of us. Everybody has to be on board and on the same page. And that leaves us with this final massive question. The technology is getting closer, and the need to decarbonize is undeniable. But when you consider all the immense challenges of governance, security, and public trust, is the world truly ready to take this leap and kick off the next great maritime evolution?